Hi, welcome back. We're going to start solving some free fall problems. Here we go. So when it comes to solving free fall problems, let me give you a couple notes on this really quickly before we go. Like I said in the previous video, because I just said it like 30 seconds ago. There we go. Free fall this is so strange. So when I use text-based relay, I get this lag. If I use anything else, it's totally fine. It's so bizarro. I have to be a little closer. So free fall. So when it comes to free fall, first of all, free fall is under constant acceleration. This allows us to use the kinematic equation. So we're going to use this toolbox to help us solve it. Our favorite equation. So like I said, the first two right here are my favorites. Those are the ones I use the most because I just think they're the simplest to solve with. These are okay. This one's fine, but usually you don't have all this information. It's usually a little harder than this. On this one, the problem with this one is that it's quadratic, meaning that if I had to solve for time, for example, this and this, you would have to rearrange this to make it look quadratic. So this would be negative delta x. Notice that I brought this over, plus VIT plus 1/2 AT squared. And then you would have to use that b squared plus or minus the square root of b squared minus 4ac over 2a, or you just Google it and look it up and just type it into some function generator online, because that's, let's be real, that's the easiest way. Because of that, I don't like this equation, because I don't want to solve quadratic. I just guess I'm being lazy. I'll leave it there just in case you need it for reference. So you need the quadratic. And this is for solving t only. You don't have to use the quadratic for anything else. It's just t, because t, you have t squared, and t, you have two parts where t is located. Second, which I've already mentioned, but I'm going to mention again just to be super repetitive, is that a now has a fixed value. In all of the free fall problems, we have a. So, woohoo, woohoo, and woohoo. Notice that, again, my two favorites. A is in there. That's one thing we already know in the question. Pretty good. This doesn't have a, so that makes it a little harder. And then this one has the quadratic, so that's why I personally like these two. So it's totally personal preference. You can use whatever you like. Okay, so here we are. We're going to answer that question. Does a penny... Basically, I'm asking how fast is it going. Lethal's kind of morbid, I guess, but... But, I know when I was first learning about physics, someone would mention that. I'm like, I don't know. It would go pretty fast. Is it fast enough to hurt somebody? I don't know. So, we can figure it out. Let's do it. So I went on Google and I looked up the approximate height of the Empire State Building. So this is the approximate value of that. So ignoring air resistance, big factor here. How fast would the penny be, or how fast would the penny move right before it hits the ground? So I'm going to move this a little closer, so hopefully I don't get so much of that lag that I'm getting here. Let's fix me up here. Okay, there we go. All right, so even though there's a beautiful picture right there, I'm going to draw my own picture because I can't stress how important that is. So what you're going to do is you're going to draw your picture. Here's my Empire State Building. I know the Empire State Building is this tall, like this. And then we're going to have the person and the obscenely large penny, just for, ease of drawing. We know that, let's see. So the penny is dropped. So dropped is a key word for the initial velocity of 0. So that means VI is 0. Like that. So I have the initial velocity. And then you're like, I have one number and you want me to solve what? So, good question. What do I want to solve? I want to find the final velocity before it hits the ground. Once again, I've mentioned this before, is that we want the velocity before it hits the ground because once it does hit the ground, it's no longer in free fall, which means we can't use these equations. So some people are like, ha, gotcha, it's 0. You're right, but you can't model it that way. You can't model, in other words, you can't find out how fast it is before it hits the ground without the acceleration right here. So anyway, point is, I don't want 0. I want how fast they're going. So I have VI, I'm looking for VF. So let's make a list of our variables because I like to do that, even though I have them written there too, because I think it just makes things so much more clear. I'm looking for VF. I have, so the penny falls this distance, right? Notice what I said, falls, right? So the motion of the penny is down. The displacement of the penny is lower than when it started, which means this has to be negative. The penny has fallen. We're not modeling the height of the building. We're modeling the motion of the penny. Very important. People forget this negative sign. It completely messes up your problem. And, like I said, we have that the acceleration, due to the fact that it's in free fall, is 9.81 meters per second squared. VI, VF, X, and A yields this equation nicely. And then we can go ahead and plug in our values and solve for our unknowns. And there you have it. So now I'm going to go ahead and simplify things. So I'm going to take some shortcuts. So that means that this is 0. So that whole term goes away. So essentially what I need to do is do 2 times 9.81 times 381. 2 times 9.81. 2 times negative 9.81 times negative 381. I am taking those negative signs. And that's important because this becomes a positive value. So I get 7, 4, 7, 5.22. I can't believe how much this thing lags. It's like awful. I'm just mad because I know I could use a different recorder and it doesn't do this. So bad. Okay, like that. Now I have to square root both sides to get rid of that square root, so I'm going to go ahead and do that next step too, to solve for VF. Man, I'm just losing my mind on this because this thing is just awful. I think let's see, it's 86.5 if you do that. Now if you get like 87 or 86.67, I'm going to round this to 5. That's fine. I'm going to put my pen in here and see if that helps a little bit too. So anyway, so the answer is 86.5. And then what I have to do is I have to add the sign back in because of this, the nature of a square root, right? A square, the value can be positive or negative and it gets rid of that value. So I have to go back and put that in to model the downward motion of this object. I will tell you that 80% of you will forget this and 80% of you will lose 1 point on your exam. Not because I'm trying to be mean. It's just a very small detail that people forget. But remember, we're modeling the motion of the penny. It's going downward right before it hits the bottom right there. So, so first of all, the negative means it's down. 86, that's in meters per second. So just fun fact, if you're curious, you don't need to know this conversion. But this is about 170 miles per hour. So if you want to question whether or not it's lethal, I think the answer it is. It's pretty fast. So the good news is that what happens in reality, though, is there is air resistance, and the penny reaches terminal velocity, which means the push up from the air equals the weight of the penny, happens at 60 miles per hour, which is not comfortable. So you wouldn't like that, but it wouldn't be lethal at that point. So still not a good idea to throw a penny off the building, in all essence like that. Okay. How long is the penny in the air for? So this is fun. Since we're modeling the same motion, this downward motion from here to here, all of this information is usable because we're modeling the same situation. And in fact, it really doesn't matter what equation you use to solve for time. In fact, anything with time in it would be fine. But like I said, I have my favorites. I'm going to use the one with the time as my favorite one. Oops, sorry about that. I'll fix that. There we go. So VF is equal to VI plus AT. It's my personal favorite. And then the final velocity is the number that I just got, equal to the initial velocity, which is 0, plus negative 9.81. So the acceleration is still that negative 9.81 times t. I'm going to divide, this is 0, so that goes away. So I'm going to divide both sides by 9.81. The negative is important because it gives us a positive time. I get 8.81 seconds. It's a long falling time. Cool. So that's the time of your penny. Like I said, this one's pretty plug and chug. I think I gave you a plug and chugga. I'm just being silly. A plug and chug type of question on your homework. So you have at least one. But this one's different. You throw this one up. So this is a thrown up question. You throw it up with a speed of 7 meters per second. So you throw the object up. So I don't know, let's make a, I don't know, what do I have? Ball's boring. Let's throw an apple. Let's throw an apple today. Let's color in our apple. Let's give it a nice little green leaf. There we go. And the stem. Oops, can't be the same color. Okay, good. Alright, so we're going to throw this apple up. At 7 meters per second. The questions are, how high did the apple go? How long was it in the air for? How fast is it going at 1 second? And how high is it at 1 second? Okay. Draw a picture. This question goes beyond the words that are here. Meaning that, think about what happens. If you take an apple and you throw it up, it's going to come back down. Now, it doesn't say it goes lower than what's supposed to. So, we could assume that it comes right back down. So this apple is going to travel up and then back down, right into the same spot. So, part 1, determine the maximum height. So, if you think about it, the maximum height happens halfway in its motion, right, from here. This is the maximum height. Things are getting a little crowded here. Because the full motion's up and down. So max height at half motion. That's true for projectiles when we do that next. Which means we need to focus on this point from here to here. Although I drew a very lovely apple. Kind of want to draw it somewhere else. Oh, it's such a good apple though. Let's draw it really quick over here. Second apple drawing of the night. There we go. Yeah. Okay, so the point is that it starts off with an initial velocity, right, because we're throwing it upward at 7 meters per second. We don't know how high it's going. In fact, that's what we're looking for. And here's beyond the problem, like I'm talking about, is at the very top, the object stops. So V, I can call this VF, even though that's not the final motion technically. Physics equations don't tell you what to do. You tell the physics equations what to do, right? I always like to say that, you can't look at a hammer and say, okay, work. You have to pick up the hammer and use it. So same thing with equations. You tell the equations what to do, not the equations tell you what to do. If you understand that early on, things will be better. So I'm going to call the top my final point. I have an initial, so look at my layout, right? I have the initial is 7, positive because it's moving up. My final is 0. My delta x is what I'm looking for, and my a, which is not given, but we know it's given because we know it's free fall, is negative 9.81. Once again, to the rescue is the best equation ever. It's this one. So 0 is the final, 7 is the initial, plus 2, negative 9.81, delta x. So 7 squared is 49, and I have to subtract that out. So negative 49 meters squared over second squared equals negative 19.6 meters per second squared, because I combined and did 2 times 9.81. I just memorized that because this just happens a lot. Delta x. This is where I do need a calculator. So to get x by itself, I divide both sides by negative 19.6, where I get delta x is equal to 2.5 meters. Notice a cool effect about this. Notice that it's positive. It says the apple has risen to this height. Pretty cool. I want you to know that this is not the only way to solve it. The alternate method, you can solve this, is to use this equation. Oh, we don't have the time. I'm sorry, you cannot do that. You can if you do part B first, but that's all right. Pretend I didn't say that. Okay, total time in the air. Now we need both motions. We can't just go halfway. We need to go up and back down, right? So this is all part A. Part B. So the apple goes up and comes back down. And I want the time for that. So what I can do is say the initial velocity is 7, which is true, and change my final velocity to negative 7. Assuming we're catching it in the same spot, you can make that assumption. So by choosing my endpoint here, I have the full motion, right? The up and the down. Velocity final is negative 7 because it's moving down. The initial is positive 7. The acceleration is negative 9.81, which makes t my variable that I'm looking for. And we're going to go ahead and use this equation. Like I said, they're just great. Here's a red flag. The 7s do not cancel out. They look like they do because they are opposite each other, but if I'm going to solve this, I actually have to subtract 7 on both sides. That goes away, but this adds up to negative 14. Negative 9.81 times t. T will equal negative 14 divided by negative 9.81. 1.43, I can round. like that. So that's our time. That's the total time. That's the up and the down. How fast is it going at 1 second? This one throws off people. But if you treat it as the following, you say your initial velocity is 7 meters per second. Our acceleration is negative 9.81. And we know the exact time of 1 second. We can figure out the final velocity. So this tells us how fast we're going at a particular time. Having the time is actually fantastic because you can do things like this. You can figure out exactly how fast it's going. So 7 meters per second plus negative 9.81 meters per second squared times t. I'm sorry. T is times 1 second. So this becomes times 1. So basically this becomes 7 minus 9.81. My velocity becomes negative 2.81 meters per second. The negative means we're moving downward. So actually what it tells me is I am falling at this point, right? What do I mean by falling? The ball rises and falls. Now, my final speed is negative 7, so I fell about 2 meters per second, so I'm probably somewhere up here at 1 second. Because my velocity is negative 2.81, or maybe a little lower. But that's what that means. It tells me my velocity. If this thing were positive, then this would mean it's rising. So I could ask questions like that. Those are fun. Is the ball rising or falling? Depends on this velocity right here. Is it positive or negative? And then it wants us to know, part D, is where is it at that time? So this is when this equation does come in handy because I have time. I don't have to use the quadratic. So where is it at 1 second? Where is it? It's the delta x. So the initial velocity is 7. The time is 1 second. Plus 1/2 a t squared. There you go. This becomes 7 meters, sorry. The seconds cancel. 0.5 times 9.81 times 1 gives me negative 4.905. 7 minus 4.905. My displacement is 2.095 meters. Above, so the positive means I'm above where I started, so that makes sense. What did we say the maximum height was? 2.5. Yeah, we're actually very close to the top, 2.05. So actually, it should be up here is where that actually occurs. So, what was my total time? 1.43. Okay. Yeah, okay. Everything seems to check out. Just double checking here. All right, great. Cool beans. So that's how you solve that question. They do get repetitive. I hope you notice that. If they're getting repetitive and boring, then it's good news. Okay, now we're combining motion. So just like that rocket car kind of question, this is a very similar type of question. In that this has multiple motions. So imagine there's a person on a balcony. Oh boy. Draw a boy. Let's draw a boy. Let's draw a baseball capped. Okay, here's a boy. Got ears. Let's see, a boy on a balcony throws a ball straight up. Oh gosh, I highly regret drawing a person. Lego person throws a ball. Red ball. They're in a balcony, so, you know, we don't see the rest of their body because, let's face it, I'm not sure if I could draw it. They're on a balcony. A building. I don't know, I'm amused by my I hope you are too. Or you're just annoyed, I don't know. Okay, so we have the boy in the building. In fact, actually, we should make it a little taller because we know the balcony, the balcony is 25, and this distance is so small, so let's pretend that's part of the distance. I drew it. We know the balcony is 25 meters tall. The boy throws it up at 20 meters per second. It misses and goes down. So the trajectory of the ball would be up, and then down like this. Misses the balcony on the way down, and eventually it's going to come to the ground, right? So this would be the green grass on the ground. So that's what's happening here. Now, people miss this part, misses the balcony, so just careful with that. You know, rereading the questions is really helpful several times, all that fun stuff. So basically what I'm going to do is combine motions and show you what I mean by that, but most importantly, I'll just tell you that one equation will not solve the whole question. You know, it's not a plug and chug. You got to organize things and figure out what we have. And by the way, you don't need to do part A first every single time. If you find part B first and then part A, it's okay. In fact, you can actually do part C too. These are all little fun things that you could do with that. So just know the order at which you solve things doesn't matter. Let's see. Do I want to solve it out of order? I could. Nah. I like going in order, but you can't solve it out of order. Some people get, you know, like, oh my gosh, I solved it B first. That's okay. So first I'm going to start labeling. So I know that it's moving at 20 meters per second, you know, at the beginning. So here's a really helpful trick. Right here, where my dotted line is, notice that's where that's the same position of the ball. That at this location right here, where I have the dotted line, is negative 20 meters per second. I know the velocity will be 20 meters per second at the same position right here, even though it's going up and down because of that symmetry thing I was talking about. I also know at the very top right here that this is 0 meters per second because it stops. So there's two pieces of information I got from this problem without the numbers given, right? So that's a really important thing to do. So the maximum height of the ball is basically going to be 25 meters plus however high this ball goes, right? So again, just pretend that a person's arm is not this far off from the balcony. But I'm going to solve for essentially delta x in part 1. I hope you notice that it's very similar to what we did earlier. In fact, it's the same. So I could say VI is 0. Kidding. I mean, I could, but I'm not going to do that. VI is 20. Yeah, that's fine. I could do it the other way, but I think this is more straightforward. Remember, we have A, despite the fact that it looks like we don't. And we solve for delta x. So what do we have here? This is a good equation to solve for this. So then we have the final velocity is 0. The initial velocity is 20 meters per second squared, so that's going to be really fun. Plus 2, negative 9.81, delta x. This becomes 20 squared is 400, so I'm going to take that is subtracted over to this side. So I have negative 400 meters squared over second squared is equal to 2 times negative 9.81 delta x. So like I said, I memorized the fact that 2 times 9.81 is negative 19.6 because it comes up a lot. And then I'm going to divide both sides by negative 19.6 to get x by itself. And when I do that, 400 divided by negative 19.6, my delta x is 20.4 meters. So, I mean, it depends. It says, you know, what does it say? The maximum height of the ball. So if we're doing it relative to the person, it's 20. But if we do it relative to the ground, it will be 25 plus 20.4, 25.4 meters relative to the ground. So it doesn't really specify, but both of these are correct in modeling the situation. Then we want the total time in the air. This one is a tricky one because of this feature. Yeah, okay. Let's think about a different way to solve it, but this one's tricky because technically we don't know the velocity down here. We don't know VF. This makes things challenging because right now our choice is to solve part B is to do the delta x equation, which we can. We can do this. But then I have to use the quadratic because then we're solving a quadratic equation. So I'm like, I don't do that. I can. Perfectly capable of doing that. So what I'm going to do actually for part B is I am going to use this one because I like it and skip to part C and find final velocity and then go to part B. So now I'm going to do that switcheroo. So part C, my initial velocity I could say is 20 meters per second. My acceleration is negative 9.81. Here's the fun feature of this. Delta x is going to be 25 negative. Okay? Let me explain why. It's not 40. That's a distance. We're looking at displacement. The object started here. Regardless of what it did, it ended on the ground. The displacement of this object, delta x, or I guess would be from where I labeled it right here. Delta x right here starts here, ends here, so it is lower than when it started. So the displacement is negative 25. It doesn't, if I wanted to know the distance, that would be the up and the down. But that's not what we're trying to find right here. These always use displacement. What am I solving for? Final velocity. There we go. Okay. So with C, I can solve for final velocity using this. The initial velocity is 20. Negative 25. And many people get hung up on that, which is tricky. You know, you see the object go up and down, and you're like, well, why aren't I using that whole distance that object's going? Because of that, it's distance, not displacement. We want to model its motion from start to finish, not its total up and down. So if you notice, as I was talking, I simplified both of these. And I'm going to simplify them again. So this is 890.5 meters. that is v squared, so I have to square root both sides to get the velocity at the bottom. .14 is the velocity at the bottom. Did I mess up something? No. 10 times that times 2. No, that's okay. All right. I'm okay. Yeah. Yes, I did. I knew I messed up something. I did. It's in my calculator. 890.5. That's why. I was like, it should be faster. I was right. Trust my instincts. 8.4. There we go. That's better. I remember it being close to 30. Cool. So that's a velocity right before it hits the ground. So now that I have the velocity right before it hits the ground, I can now use this one instead to find time because it's just easier. And remember, I have to put that negative back in. So negative 29.84 meters per second equals positive 20, because that's what we started with, plus negative 9.81 t. So I got to subtract the 20 first on both sides, which negative 29.84 minus 20 gives me negative 49.84 equals negative 9.81 t. Divide both sides by negative 9.81. And I got t is 5.08 seconds. And that's the total time of flight. Time of flight. Like that. Alrighty. And there you have it. You'll definitely have a question like this on your homework. So, yes. So this one is the same problem. So what I'm going to do is actually I'm going to skip it. I'm not going to solve it again. You solve it. I'm not going to quiz you on it or anything, but it's a really good way to take a break and try it yourself, see how far you get, see what you don't know and what you don't understand, and rewatch the video and try to come up with the answer. I'm pretty sure the answer is in the, in the, what is this thing called? The note sections of your PowerPoints, so you can try this one out. But we'll do a lesser known one. Let's see this one. A rock is thrown directly upward from the edge of the flat roof of a building that is that tall. The rock misses the building on its way down, and it served to strike the ground 4 seconds later after being thrown. Okay, what was the speed the object was thrown? Okay, so we're working a little backwards here. Ooh, fun. And we're on top of this building. You know, the building's 56.3 meters tall. We knew that the total time for this up and down is 4.00 seconds. We don't know the velocity at which it was thrown. We don't know the velocity at which it strikes the ground. But we do know a... Okay. So, actually, this is similar to what we just did. We have the total time. If we have the total time, actually, even more fun, we have the displacement. So the displacement, the object started at this location and ends down here. So this delta x is negative 56.3. So in fact, here's where this equation is super helpful because we have time. Remember, this equation is not bad if you have time. And in fact, it has the variable that we want to solve for. So check it out. negative 56.3 meters equals VI is what I'm solving for, times 4 seconds. It takes 4 seconds to do this displacement. That's what this means. Now I know, again, it feels weird that you're like, what? It's going up and down, but you're saying displacement's that. Well, the time covers the up and down here and that. And then we have this layout like that. So this becomes a fun algebra problem. So I'm going to rewrite everything. I'm going to leave that as this. And I'm going to go ahead and simplify this step. So 4 squared times 9.81 times negative 9.81, by the way. So I get negative 126.61 meters when I do that. I have to get V by itself, so I have to add that over. So I'm going to do negative 56.3 plus 126.61. And then I get 70.31 meters equals VI times 4 seconds. Divide both sides by 4. I get an initial velocity of positive 17.58, which seems to be like a pretty reasonable number. Looking good. All right. Okay. So there you have it. Several different types of problems. Not all one size fits all. Very important to model your direction of your signs. You'll definitely see problems like this, and I'll just advertise now that I like problems like this one on your exam because instead of, I'm not looking so much that you can plug and chug. I'm looking to see if you can analyze a question. So you'll have, if you have plug and chugs, there'd be like a multiple choice question. But this tells me what you know about physics. So in terms of studying the exam, I want you to know questions like number 3 right here. I mean, the other ones are valuable too. I'm not saying they're not because you need them for understanding. But if you had to focus on something and your time is precious, that would be this type of question is something that I'd like you to think about and learn when it comes down to the exam question. If you have any comments, of course, please feel free to leave them in the comment section of this lecture slide, and I'll get back to you. And if you have any questions, let me know. And best of luck with free fall, and I hope that it was at least entertaining. Have a great evening, everybody. I'll see you in the next video.